There. Okay, so we're just going to do some examples from Chapter 2 that will help you with the test. So a general vector is just x, y, z. So if we're given a vector, and suppose I said to A, find the span of the column vectors in A. So if we were to write the columns as vectors, equal to a general vector, what we're looking to find is what kind of vectors can we get as answers? Like, does the vector 1, 1, 1, is that a possible answer to this? And that's what the span is saying. What are all the answers? Way back in Chapter 1, I said that the span is like the range. It's the answers that you can get. So when we're looking for the span, it's saying, can I put any x, y, z in here and it give me an answer? That would mean that it spans R3. That means any vector. So what we're going to do is find whether or not this spans all of R3 or if it spans some subset, some smaller set of R3 with some formula. So you would set up your matrix as an augmented matrix with the general vector. So that is that we say A with, a general vector. We augment that. And then we row reduce. So this one is not very nice, but we want a 1 in this top corner. So row 1 is row 1 divided by 3. Okay, and now we want zeros. So row 2, that's a -3, so we want the 1 to be a +3. 3 row 1 plus row 2. We already had a 3 there, so I'm just going to write that down. 3, 5, 7x. Right, because that is row 1 multiplied by 3, plus row 2. Add them together. And so x plus y is just x plus y. And then row 3 is a 6, so we want the 1 to be a -6. Same number, opposite sign. So -6 times row 1. Would be -6 -10, -14, and -2x. Plus row 3, 6, 1, minus 4z. 0, minus 9, minus 18, z minus 2x. Okay, so if we write those in, 1, 5 over 3, 7 over 3, x over 3. Okay, so now when you're doing the span, we're actually worried about a row of zeros at the bottom. We want to know if there's going to be infinitely many solutions, which would be a row of zeros. If there's not a row of zeros, if there's a lead 1 for each row, then it's one solution, and that would span R3, because we would have x equals the number, y equals the number, and z equals the number. What we want is this last row to be all zeros, which it's going to be in this example because I can see that there are multiple. But anyway, let's keep going. So this is in row 2, and I want to take row 2 and divide it by 3. Okay. Now, all of that, what I just said, is basically worry about the bottom, don't worry about the top where there's already a lead 1, worry about this bottom row. So let's just get rid of that -9. You don't need to really do anything with the top row. So, if we were to get rid of this -9, that's in row 3, the -9, so we want a 9 times row 2 plus row 3. So 9 times row 2. 0, 9, 18, and 9 times x plus y over 3. Which is what? 3x plus 3y. Because the 3's cancel, you have 3 onto x plus y. Okay, plus row 3. 0 minus 9 minus 18, and z minus 2x. Okay, so if we add those, 0, 0, 0, 3, we're adding all this together, so 3x plus 3y plus z minus 2x is what? Zero, 0, 0, 1x, so x plus 3y plus z, is that right? Okay, so here it is. I don't need to make the 5 over 3 0 because I'm not solving the system. I'm looking for what the span is. What kind of answers can we get? You're looking for this row of zeros at the bottom. That's what's important. So this has no solution for most numbers that I'll plug in here, because if I put x, y, and z as just any vector, I put 1, 1, 1, what do I get here? 5. Well, 0 equals 5 doesn't work. That would have no solution. How would this have a solution? If this stuff added together to give 0. So if they were all zeros, that would work. But is there other possibilities? Sure. What if I put a 3 here and a -1 there and a 0 there? A 3, a -1, and a 0. Doesn't that equal 0? And then I'd have a row of zeros, and it would have infinitely many solutions. There's lots of possible answers. All of the answers that work are the span. So what did I just say? I just said 3, a -1, and a 0. So that one works. 3, -1, and a 0 works. And there's others that work. Plug in any two, either x or y or x and z. What if I said that x is 1 and y is 1? What would z have to be? If x was 1 and y was 1, and I need that to equal 0 for it to have a solution, z would have to equal -4. So that's another possibility. And I could go on forever plugging in any two and get an answer. All of those vectors together make up the span. But you have to put it as a general vector. So we're saying that x plus 3y plus z has to equal 0. So if that were true, then the answer, whatever we plug in, will work. So x has to equal -3y plus z. Solve for one of them, it doesn't matter which one. Here's our general vector, x, y, z, and I'm saying that x has to be -3y plus z. So since these are on the other side, these are free, This is a lead, only because I solved for it. These are free. This is the form. So I could plug in a y and a z and then find the x from that.
Isn't it supposed to be minus it?
Oh, yeah. Yeah, when I move it over. Thank you. All right, so y and z are free. All right. So we would say the span of the vectors 3 minus 3, 6, 5 minus 2, 1, and 7 minus 1 minus 4 is equal to minus 3y minus z, y, z. Or you could have a's and b's, it doesn't matter what letters you have in here.
Points that we don't write it in that format, like put the span.
No. This is just the proper way to write it, but if you don't write it exactly like that. You could also say this is as a linear combination. So minus 3y, 1y, 0y's, and z is minus 1, 0, 1, which are both vectors in the span as well. So the span is, since it has two free variables, the span is a plane. So it gives all the possible vectors in that plane will work. You could have just one free variable. Now, are the vectors, or the column vectors, in A dependent or independent? Without doing any work. We already row reduced it. If you were going to do dependent and independent, you would row reduce it, but instead of a general vector on the other side, what would you have? You would still do the row reduction the same, because you're only ever reducing, oops, that's a 1. But on this, you're only ever reducing this part, so you would row reduce the same way, but you have zeros here, so you don't need to row reduce again to figure this out. If we were to do the row reduction, we have it partially done up above. Instead of these x's that were over here, we would just have zeros, because anytime you add a 0 or multiply by 0, it stays 0. So is this dependent or independent? Dependent means the answer has a free variable. Does this have a free variable? Well, there's a lead 1 here, and there's a lead 1 here, and is there a lead 1 for the z? No. This one's free. So it's dependent. If there's a free variable, it's dependent. It means there's infinitely many solutions. There's more solutions than just 0, 0, 0. Although 0, 0, 0 works, there's a lot more solutions that will give an answer to this. Yep.
In terms of the general vector for the span, can you also use x and y to represent that?
Yeah. So in here, instead of y and z, you could solve for any of them and plug it in any way. Yeah. And you could actually put like R and T or A and B. It doesn't actually need to be those letters. It just has to be any two letters here and this. So what I'm saying is this, you could write minus 3A minus B, and this is A and B. Right? That would also work. It doesn't really matter. The other thing, that if we went right back up here to where we solve for x, if you would solve for z, then that would be in the last one, and then these would be your A and B. If you solve for y, then the y would have a little equation, and so you could actually solve for anything.
How would you write an appropriate linear combination? Is that just like write one possible solution?
Right. So you would write to write a possible linear combination. I didn't finish row reducing this, so we don't actually have a solution, but we could find one. So let's say we wanted to find a linear combination. How would we finish this? What needs to be done to finish that?
I bring it to class today, I don't know how to do it.
The top one.
That one, it's not very nice because it's a fraction, but row 1, so this would be minus 5 over 3, row 2 plus row 1. There's lots of zeros, so it's not actually that hard. Minus 5 over 3, row 2. Plus row 1. So 1, 0, minus 1, 0. So let's write the solution. So you could have x, y, z, a, b, c, it doesn't matter what letters you have here. So x minus z equals 0. Y plus 2z equals 0. So x equals z, y equals minus 2z, and z is, of course, free, so x equals t, y equals minus 2t, and z equals t. Does that make sense? All right, just writing our solution. So a linear combination, originally we had the vectors 3 minus 3, 6, 5 minus 2, 1. I'm just leaving space to put the linear combination, so don't write these down yet. So when you're doing dependent or independent, you have equal 0 on that side. And so what we found is x is t minus 2t plus t equals that. That would be possible with t's in there. You could put a number in for t. Say we let t equal 5, then what would we have? 5 times that minus 2 times 5 is 10. 5. Right, you could put t is anything into it, or just leave the t's, and it would be an appropriate linear combination. Most people just put 1 in for t. Don't put 0, because you're trying to show that there's other solutions other than 0. 0 always works. Most people will put, like, t is 1 in. It's easier to check your answer if you put t is 1. All right, so 3 minus 10 plus 7 is 0, so on. 6 minus 2, oh, what do I have wrong?
Yeah.
Oh, I probably just wrote, I just rewrote that from the other page. Yeah, there we go. Rewrote the vector wrong. Okay, so let's say we have okay? So we want to find the general span of this. So you would say this is as a linear combination. And to ask for the span is asking, if we make this combination, what kind of answers can we get? set it up. With X, Y, Z, and then you row reduce. Now I put some ones and zeros in here, so hopefully it will be easy. But again, when you're looking for the span, you're really looking for the lead ones. There's a lead one for the first row, so we don't really even need to ever change the rest of the first row. What we need to do is rearrange this so that we can see if there's a row of zeros or not at the bottom. So, first step would be to make this into a 0. So that's in row 2. It's a 1, so this needs to be a negative 1. Add row 2. 0, 7, minus 2, y minus x. So you should be able to see right now that row 2 and row 3 are similar on that side, so they will end up being a 0 there. Right, a row of zeros, right? So you just need to get to that. You can see that it's there now, but we just need to get to it. In fact, I don't really even need to make a 1 that's 7. I could, but I really don't need to, and it's easier not to, because if I just want this to be a 0, that's in row 3, it's a negative 7. Row 2 has to be a positive 7, it already is. So row 2 plus row 3. So I'm adding these. That's a 0, that's a 0. What would I have here if I add them? Z plus y minus x. Right? Here's going to be a lead 1. If I divide that by 7, I can get my lead 1 here. So there's a lead 1, the lead 1. This is a free variable. So right now I can conclude that it's dependent if it asks that. If it asked me to continue on and find the actual linear combination, I'd have to just stick zeros on this side and keep reducing. Okay, but I'm asking for the span here. So for the span, this is my condition. For this to have a solution, z plus y minus x has to equal 0. So I can solve for any of these letters. It doesn't matter which one. So let's solve for z just because it's in the start. So x minus y, do you agree with that? I didn't make a mistake that time. So our general vector, x, y, z. Z I'm putting as x minus y. And the other ones I don't need to do anything to. So there it is. So what if I said to list 3 vectors in the span? What would we do? Right. Pick x and y. So, well, one vector in the span would be 0, 0, 0. That will always be. What else? What if I put a 1 and a 1? X minus y, 0. What if I put a minus 5 and a 2? Minus 5 and a 2. Minus 5. Minus 2, negative 7. When I was making up the vectors, when I made up the question, that's what I did. I said that minus that is 0, that minus that is minus 7. I just stuck 2 numbers here and I subtracted them to get the third. That's exactly what I did when I made them up. That's why Newt would have span. Yep.
In the previous example, you said z equals t. How do you determine what is t?
Well, t is any number, but that was when we were doing the dependence relation. That has nothing to do with the span, because the answer is different for the span. The span is telling us what kind of answers we can have here, right? So anything that is of this form, and I plug in numbers, I can get a possible vector that if I made a a system of equations with these three vectors, and then the other vector on the other side, it'll work. If I take one that's not in the span, like 0, 3, 14, that one's not in the span, and I set that up as a linear combination and try to solve it, it'll give no solution. This is not in the span. So only the vectors that are of this form will work with those equations. When I did that T, which isn't necessary, I was asking for a dependence relation. Okay, or to write an appropriate linear combination, right, for the dependence. So if you had to do that, you would go back to what you have. We've already reduced it partially. And instead of the x, y, z, stick 0 on the end. Finish row reducing it. Your solution will give you your dependence relation. So how do we finish solving this? We might as well do it. So this, of course, needs to be a 1 if we're going to solve. And then the -5. So that's a -5. Row 2 would need to be a +5. Okay, so this is x, y, z. So you finish row reducing it, and then write out your solution. So our first row gives us what? X minus 10 over 7. X minus 10 over 7z equals 0. And the second row gives me y minus 2 over 7z equals 0. So x equals 10 over 7z. Y equals 2 over 7z, and z is free, so x is 10 over 7, y is 2 over 7, and z is, so we use those, or any multiple. So what multiple would be logical to use there? What would you let t be to give nice numbers? 7. Instead of 1. You could put a 7, then you would have some nice numbers. So, one example.
Is that just whatever the free variable is?
Yeah, we're just solving the system. That's a normal solving the system. Oh, 7. So x would be 10, y would be 2 times 7 over 7, and z would be 7. So 10 times whatever our first vector was from earlier, 2, 7, and this is your dependence relation, or an appropriate linear combination. So maybe not as interesting, if you find this interesting at all, maybe not as interesting would be if I said to find the span. I'm not going to row reduce again, but find the span, and I gave you 3 vectors. I don't know what they're actually gonna row reduce to, okay? But say we put those in. With your X, Y, Z. Okay. I don't know the exact answer, so just don't say that this is true. It might have a span, but say we get a 1, okay? We get a 1 here, and we get a 1 here, so these could be anything. Okay? So say we end up with this. I didn't change row 1, but yeah, and it's probably going to be something weird here, but say I get this, okay, and these little stars just mean they could be anything. They're not all the same, they're just whatever. Do you see there's no row of zeros? When we were doing the span, we were trying to get a row of zeros at the bottom. If you don't get a row of zeros, that just means it spans R3, which means there's no condition. Just put any vector at all in and it would work. And so you could try this, and I'm pretty sure this would reduce it and give you something like that, okay? I'm just saying I'm not positive, but I just did it quick. Put numbers in that I think would work. So if you get all lead 1s, then there's no condition. So it will always work, and it'll always have a solution. Okay? So then we would say it spans R3. Which is just any vector in R3 at all that you can make up will work with that. And it also would mean that it's independent. There's no free variables. Which means there's no appropriate linear combination because there's no answer that would work other than putting zeros here to equal 0. Nothing to do. Okay, because if you get all lead 1s and zeros on this side, then that is the only solution. Okay.